Every 22 seconds, somewhere in the crowded shell of low Earth orbit, two satellites pass close enough that a single mistake would end them both. That is not a crisis. That is a normal, healthy day up there. And that is the problem. In December of 2025, astronomer Sarah Thiele and her colleagues published a number they called the crash clock, and it revealed how little room for error we have left. This is the story of a machine we built above the world, the margin we quietly stripped out of it, and how few days now stand between order and chaos. Right now, several hundred kilometers above your head, there is a machine running that almost no one thinks about, and it never stops. It has no single building, no control room you could point to, no operator you could name. It is made of thousands of satellites, each one adjusting its own path, and thousands of engineers on the ground watching screens, and a web of radar dishes and command links stretching across every continent. Its only job is to keep the objects in low Earth orbit from hitting one another. And for the most part, it works so well that you have never once had a reason to notice it. That is the strange thing about the sky above you. It looks empty. On a clear night, you see a few moving points of light drifting between the stars, and they seem calm, orderly, almost serene. But that calm is not the calm of an empty room. It is the calm of a plate spinner who has kept every plate in the air for so long that the trick looks effortless. The moment the spinning stops, the plates do not slow down. They fall. For decades, we told ourselves that the danger up there was a problem for the future. A mess we would clean up eventually, the way we always promised to clean up a mess. We were wrong about the timeline in a way that a small team of astronomers has now put into a single, uncomfortable number. And to understand that number, you have to go back to a warning almost no one listened to. In June of 1978, two scientists at NASA's Johnson Space Center in Houston published a paper that most of the world ignored. Their names were Donald Kessler and Burton Coore-Pallet, and the title was as dry as science titles get: Collision Frequency of Artificial Satellites, the Creation of a Debris Belt. What they argued inside it was not dry at all. They had studied how the asteroid belt grinds itself down over billions of years, one collision feeding the next. And they realized the same physics was quietly waiting to switch on much closer to home. Every satellite we launched into low Earth orbit added to a population of objects moving at enormous speed. Sooner or later, some of them would collide. Each collision would shatter into fragments. Each fragment would become a new projectile, raising the odds of the next collision, which would make more fragments, which would raise the odds again. They predicted that by roughly the year 2000, our own debris would overtake natural micrometeoroids as the greatest impact threat to spacecraft. That runaway idea earned a name, we call it the Kessler syndrome. And for most of the space age, we treated it exactly the way people treat a warning with no date attached to it. Something to monitor, something for a later generation. The picture in most people's heads, if they had a picture at all, came from films, where orbit shreds itself in a screaming chain reaction that plays out in minutes. That picture is wrong. The real process is slower and quieter than any movie, and that is precisely what makes the newest findings so hard to hold in your head. Because the scientists who built the newest warning are not describing the runaway at all. They are describing something else. They are describing how little room we have left before it could even begin. In December of 2025, a preprint appeared on the Iridium server with a title that told you the authors had chosen their words carefully. An orbital house of cards. The lead author was Sarah Thiele, a graduate student at Princeton University who had started the work as a doctoral student at the University of British Columbia. Her co-authors included Aaron Bowley, a physicist at UBC and co-director of the Outer Space Institute, and Samantha Lawler, an astronomer at the University of Regina in Saskatchewan. They built a measurement, and they gave it a plain, almost brutal name: the collision realization and significant harm clock, the crash clock. And it answers a single question, stripped of everything else. If every operator in low Earth orbit lost the ability to steer their satellites at the same moment, how long would pass before the first catastrophic collision? Notice what that question does. It doesn't try to predict the full Kessler runaway, with all its decades and all its uncertainty. It isolates one thing: the time to the first crash if we take our hands off the wheel. Think about what that means. It is not a measure of how dangerous space is on a normal day. It is a measure of how much slack is left in the system, how long the plates keep spinning if the plate spinner walks away. Thiele has been direct about what her own metric is not. A lot of people, she has said, are claiming the work means Kessler syndrome is days away, and that is not what it says. The clock does not simulate a cascade. It counts only the timescale to the first collision. It is, in Bowley's framing, a gauge of stress on orbit, and when you read that gauge across the last few years, the needle does something that should stop you cold. Start with how the system behaves on an ordinary day when everything is working. According to the paper, across all the megaconstellations in low Earth orbit, 2 satellites now pass within 1 kilometre of each other, on average, once every 22 seconds. Read that again, slowly. Somewhere above you, roughly 3 times a minute, 2 spacecraft slide past each other inside a margin thinner than a city. For the Starlink constellation alone, the company's own conjunction report describes performing a collision avoidance maneuver, on average, once every 2 minutes. Each individual Starlink satellite fires its thrusters to dodge something around 41 times a year. These are not emergencies. This is the normal, healthy heartbeat of the constellation. It is the sound of the machine working exactly as designed. And that is the first unsettling thing, because a system that has to move something every couple of minutes has no idle capacity. There is no rest built into it. Every one of those maneuvers depends on 3 things holding at once: fuel in the tank, thrusters that fire, and a working command link back to Earth. Take away any one of them, and that satellite stops being a participant in the dance and becomes an obstacle in it. The whole structure survives because we never stop moving the pieces. Ground stations send commands, thrusters fire, orbits shift by meters. It is a genuine feat of engineering, repeated tens of thousands of times a day. But a feat you must repeat without error, forever, is not the same thing as safety. And the objects these satellites are dodging are only the ones we can actually see. The ones we cannot see are a far larger problem. Here is the number that ought to be famous and is not. Ground-based radar and telescopes can reliably track objects in orbit down to about 10 centimetres across, roughly the size of a grapefruit. The European Space Agency's Space Environment report for 2025 tracks around 40,000 such objects, of which only about 11,000 are working satellites. The rest is junk we can follow. But following is not the same as accounting for everything. The same agency's models estimate that beyond the 40,000 we track, there are around 54,000 objects larger than 10 centimetres. Roughly 1.2 million pieces between 1 and 10 centimetres, and about 130 million fragments between 1 millimetre and 1 centimetre. 130 million, each one small enough to be invisible to us, and each one moving fast enough to matter. Aaron Bowley has a phrase for the worst of this population. He calls it the lethal, non-trackable debris. It is the middle band, too small to see, too small to set off a bright explosion when it hits, but big enough to punch through a spacecraft and kill it. A fleck of metal the size of a fingernail, moving at 7 kilometers per second, carries the energy of something you would never stand in front of. At those speeds, a paint chip is a bullet. And unlike the objects we track, there is no dodging these. You cannot maneuver around something you never saw coming. The only defense is armor, and armor has limits. The shielding that protects a crewed station is built to stop impacts, up to roughly 1 centimeter across and no larger. Everything above that line and below the 10 centimeters we can actually track falls into a gap we can neither see nor stop. We simply fly through it and hope. And this is where the danger stops being about counting objects and starts being about area. Bowley points out that every new satellite you add to orbit does not just add one more thing to track. It adds surface. It adds collisional cross-section. The more working spacecraft you put up, the larger the target you present to that invisible rain of fragments. We are not only crowding the sky, we are widening ourselves inside the crowd. And all of that is concentrated in a single, narrow band that everyone is now fighting to occupy. Not all of low Earth orbit is equally dangerous. The trouble is concentrated. The busiest, most contested altitude right now is around 550 kilometers up, and it is dominated by Starlink. That is where the density of active satellites is highest. That is where the every 22 seconds heartbeat is loudest. And it sits in the worst possible place. Because of geography, we cannot change. China's own megaconstellations are being built at higher altitudes. To reach them, their satellites have to climb up through the crowded Starlink shell. So does anything else headed higher, including missions that pass near the International Space Station. The busiest shell in orbit is also a gate that almost everyone else has to pass through. Late in 2025, that abstraction turned concrete when a Starlink satellite reportedly came close to a Chinese rocket body. These are not scenarios. They are headlines already, and a collision in that shell would not empty it in an afternoon the way a film would show. Thiele is careful on this point. The altitude would stay usable, but the operating conditions would change overnight. Far more dodging, far more risk, sustained for years, in the exact band where the most satellites already fly. An injury, not an amputation. The trouble is that we keep adding to the part of the body most likely to be hurt. There is a cruel twist in the altitudes. Below about 600 kilometers, the thin upper edge of the atmosphere still reaches, and drag slowly pulls debris down and burns it away within a few years. Nature cleans the low shelves, but between 800 and 900 kilometers, that cleaning almost stops. Debris up there can linger for centuries, and that is exactly the band where two of the worst scars in orbital history were carved. Because we have already seen what a single event does to a shell like this. And to understand why the crash clock has collapsed the way it has, you have to look at what those events left behind. 1978 gave us the warning. The real proof came later, and it came in fragments. On the 10th of February, 2009, an active American communications satellite named Iridium 33 ran directly into a defunct Russian satellite called Cosmos 2251. It was the first accidental collision between two intact satellites in history. By the end of that year, tracking systems had catalogued 1,632 fragments from that single crash, and many are still up there. 2 years earlier, in January of 2007, China deliberately destroyed one of its own weather satellites, Fengyun 1C, in an anti-satellite weapons test. That one intercept created more than 3,500 trackable fragments, the largest debris cloud ever made by a single event, much of it in that centuries-long band. In November of 2021, Russia did much the same to a satellite called Cosmos 1408, creating at least 1,500 more trackable pieces and forcing the crew of the International Space Station to shelter in their return capsules while the cloud passed. Now hold all of that beside the crash clock's central finding. In 2018, before the megaconstellation era, the team calculated that if every operator lost control at once, the first catastrophic collision would take around 121 days to arrive. Months of margin. Time to fix things. By June of 2025, that same number had fallen to about 2.8 days, 67 hours. The authors later revised their figures upward after other experts weighed in, moving 2018 to 164 days and 2025 to 5.5 days. But do not let the revision comfort you. As Samantha Lawler put it, if you think 5.5 days is fine when 2.8 was not, you have missed the entire point. Whether the honest number is 67 hours or 130, the shape is the same. In 7 years, the slack in the system fell from months to days. And the paper adds one more figure that is harder to shake than any of them. Lose control for just 24 hours, and there is roughly a 30% chance of a catastrophic collision. 1 day of silence. Nearly a 1 in 3 roll of the dice. Picture yourself up there for a moment, floating at 550 kilometers, inside the busiest shell in orbit. It would not look dangerous. That is the first thing to understand. Around you, the Earth would fill half the sky, blue and turning. The other half would be black and quiet. You would see a satellite pass now and then, a bright, deliberate point sliding by. It would feel calm. It would feel empty. But the emptiness is a trick your eyes are playing, because they are too slow for this place. The objects that could kill you are not the ones you can see. They are the fragments the size of a pea, and smaller 130 million of them scattered through these orbits, each one crossing your position at 7 kilometers per second. At that speed, you would never see the one that mattered. There would be no streak, no warning. There would be the fragment, and then there would be the hole. Now imagine the atmosphere below you beginning to swell. You would not feel it, but every satellite around you would. A storm on the sun has reached the Earth, the air has puffed upward, and suddenly every spacecraft in this shell is ploughing through thicker gas than its models predicted. Their orbits start to sag. Their predicted positions, the numbers the whole machine depends on, drift by kilometers. And every one of them, all at once, begins trying to correct. That is the moment the crash clock was built to describe. Not a movie explosion. A quiet, invisible loss of certainty, spreading through a shell you were told was safe, on a day that started like any other. And the thing most likely to start that day is not a machine failing. It is the sun. The crash clock measures what happens if we lose the ability to steer. So the obvious question is, what could take that ability away from everyone at once? The answer the authors keep returning to is a solar storm, and it is not hypothetical. We have watched it happen on a small scale more than once. On the 3rd of February 2022, SpaceX launched 49 Starlink satellites into a low orbit. A minor to moderate geomagnetic storm, the kind forecasters barely flag, arrived just afterward. It heated the upper atmosphere enough to raise the drag on those satellites by more than 50%. The team managed to command only 11 of them into a protective safe hold. The other 38 could not fight the drag, and they re-entered and burned up within days. A storm too weak to make headlines erased most of a launch. Then, in May of 2024, came the Gannon storm, the strongest in decades. During it, according to the researchers, more than half of all the satellites in low Earth orbit had to maneuver, and positional uncertainties swelled to kilometers, with everything moving at 7 kilometers per second. Lawler has called that combination terrifying, and she does not mean it loosely. Everything dodging at once, in a fog, is exactly the state the crash clock assumes. And these were the small ones. The benchmark for a truly severe event is the Carrington storm of 1859, the most powerful on record, from an age with nothing in orbit to lose. NASA and the National Oceanic and Atmospheric Administration confirmed that the Sun reached the maximum of its 11-year cycle in October of 2024, and strong storms remain likely for the next few years. Here is why this closes the loop. A severe storm is the one event that could plausibly remove maneuvering control across the whole system for longer than the margin the crash clock now measures. It is the concrete, historically real way that a number on a preprint becomes a bad week in orbit. The storm does not have to break the satellites. It only has to take the wheel for longer than a handful of days. Suppose it happened. Suppose a storm, or a software failure, or a cascade of bad luck removed control long enough for the first collision to occur. You might assume that somewhere there is an authority ready to coordinate the response. There is not. Nobody owns orbit. The framework we still operate under is the Outer Space Treaty of 1967, written when fewer than a couple hundred objects had ever been launched, in an age that could not imagine private companies fielding tens of thousands of satellites. It establishes noble principles and almost no enforcement. There is no orbital traffic controller. There are no legally binding lanes. When two operators are on a collision course, coordination is voluntary, and sometimes one of them does not answer at all, because it is a defunct satellite, or a startup with no night shift, or a spacecraft nobody will admit they have lost. Every operator makes decisions that are rational for their own fleet. Each satellite dodges the object in front of it and reduces its own risk. But no one, no algorithm, no agency, sees the whole shell at once and steers it as a system. It is too big, too fast, too fragmented. We are running a global traffic network where every driver has a different map, and some of those maps are hours out of date. This is what the every 22 seconds heartbeat really tells us. The system does not survive because it is stable. It survives because thousands of separate decisions happen to keep working out, every few minutes, all day, every day. The crash clock is a measurement of how much that arrangement now depends on nothing going wrong. And that brings us back to the number and to what it is actually asking of us. It is tempting to turn 67 hours into a doomsday clock, a secret countdown, ticking toward the end of space. That is how the number has travelled online, and it is worth being honest. That version is not true. The crash clock is not a hidden timer counting down to a collapse that authorities are concealing. It was published openly by the researchers themselves. It describes a worst case that begins only if we let go of the wheel. Low Earth orbit is not about to seal shut. The stars are not going out. The truth is quieter than the myth and somehow heavier. What the clock actually measures is our margin for error, and that margin has fallen from months to days in the time it takes a child to start school. We built a machine of thousands of moving parts and then removed almost all the slack from it, so that its continued survival now demands near-perfect decisions, from dozens of operators, every single day, with no room to recover from a bad one. Kessler warned us in 1978 that our debris could one day feed on itself. He was describing a fire. Thiele and her colleagues are describing something more immediate, how dry the room has become, and how little it would take for a spark to matter. I keep returning to that image of the calm night sky, those few serene points of light drifting between the stars. They still look effortless. They always will, right up until the moment they do not. The machine you never see is real, and it is still holding. The only question the clock is really asking is whether we will choose to widen the margin again while widening it is still a choice. Thanks for watching, and I'll see you in the next one.